Thank you everyone for coming out tonight. I know it's really hot, and I really appreciate everyone's time. My name is Soresh Kundu. I'm on the LLM training team, machine learning systems team, something like that at TikTok. And yeah, so when Arjun invited me to come out and speak, I was really excited. So today I wanted to discuss some of the things that I think about, work on, dream about sometimes at work, which is distributed training in machine learning. And I think in this new world of like LLMs, being able to train our models efficiently is of the utmost importance because the people that win in this space are the ones that will get ahead with their models. So there are really three main areas of scaling when it comes to improving AI in general. First is this idea of data. Naturally, more data is usually a good thing. But also, we want to make sure that our data is clean, so then our LLM doesn't spit out like problematic content. So there's a lot of research going on in this space regarding making data more efficient to obtain, cleaning it, and with the advent of Gen AI, even generating new data is becoming a very popular technique. In fact, this concept of distillation is really cool because we're generating new data with a larger LLM and then using it to train a smaller LLM, which naturally isn't as strong. However, it allows us to train this small LLM to specialize at a very specific task, which for most cases is probably a good thing because it's going to take less compute. The second dimension that we can optimize across are the algorithms. In 2012, when AlexNet came out, it really revolutionized how people viewed computer vision and what the potentials in this space really was. And in 2017, I'm sure you guys have read the Attention is All You Need paper when this new architecture for natural language processing came out, more specifically machine translation. Again, the whole NLP industry was turned upside down on its head as so many older techniques was simply, it was turned archaic just overnight. And then this third dimension, which we'll be discussing today, is this dimension of compute. We can scale up data, we can scale up the algorithms, but ultimately, these advancements in algorithms happen only 5 to 6 years. So in the meantime, it's always worth our time to try to be able to scale up compute in a very efficient manner. So just a little bit about me, just so you guys know who's yapping at you for the next hour. My name is Soresh Kundu. I went to the University of Wisconsin-Madison, where I finished my bachelor's degree majoring in computer science, data science, and economics. And then after I graduated last year, I joined TikTok, or ByteDance technically, in August. And I've been there ever since. So I'm on the LLM training team. Like, I don't really know what our org is called. It changes every other week. But ultimately, I'm working on the infrastructure that our LLM researchers use to train the LLMs at ByteDance. So there's two more specific aspects. First is the platform side of things. And this is essentially like the web UI that like all of the researchers use. So if you've heard of Amazon SageMaker, it's like our internal version of that. And then the second is our actual like internal training framework built on top of PyTorch that's used to train these LLMs. So I'm working concurrently on both. So let's begin things off today by introducing the main character of our story, the graphics processing unit. This thing is an absolute beast. Are there any PC gamers in the house by any chance? Anyone who's built their own computer? Okay, some of you guys? Cool. So I feel like if you're anything like me, the part that you probably thought the most about when building your computer was the graphics card. It's the most powerful, and in the realm of video games, it's probably the most important. And this is the main paradigm and the main usage of graphics cards since the early 2000s. And there's these things called shaders, which are little programs that run on the graphics card in parallel. And the task of these shaders is to be able to calculate the color of each of the pixels on your screen. And if you're a gamer with any sense of standards, your goal is 60 times a second. And maybe if you're really advanced, 144 times a second, right? For the really ultra serious gamers out there. And then machine learning researchers soon figured out that we could try to use shaders for more machine learning related tasks. But the problem is the rasterization pipeline for graphics cards was tailored over decades specifically for the task of graphics. And this made taking this awkward paradigm and stuffing it into the ML realm a little bit difficult. So in 2006, everything changed when NVIDIA released CUDA, or the Compute Unified Device Architecture. And this essentially gave researchers, engineers, scientists a very easy way to program and write C++ code that directly ran on the GPU. And this was massive because now people weren't trying to cram these awkward shaders into the world of machine learning. And the reason why the graphics card became so popular relative to the CPU, which was the original way of training these ML models, is because of its immense amounts of CUDA cores. I think the analogy that really stood out to me was if your CPU cores are like oxen, then CUDA cores, or the cores in your graphics card, are like hens. So oxen, typically more powerful, there's less of them, but chickens, they're running around all over the place. You can have tens of thousands of them and easily coordinate them. Not in real life, I guess, in this CUDA cores example. And I think this really speaks to the difference between CPU cores and CUDA cores, because CPU cores are more powerful, they're more general, whereas for CUDA cores, originally designed for graphics, are more good at specifically just adding and multiplying two numbers at a time. So going back to our timeline, in 2006, we saw CUDA come out by NVIDIA, and then in 2012, something crazy happened. AlexNet won the ImageNet competition and completely blew the competition out of the water. And the way they trained this was by using two GTX 580s, which back in the day was a huge advancement in this field. And it really showcased the community the true potential of using graphics cards in this context. And then since then, we've seen this huge boom in deep learning where everyone's trying to get their hands on GPUs. We'll have VCs trying to build GPU clusters to give to their portfolio companies, and everyone's just trying to gobble as much up as possible. So why exactly are graphics cards so useful? Well, let's look at the fundamental mathematical operation that's at the heart of deep learning, the matrix multiplication. I'm not going to explain what exactly it is. I'm sure you guys have learned this in your linear algebra class. But if we wanted to calculate the value of the exclamation point, what we need is the dot product of the first row in the left matrix and the first column in the middle matrix. But the fascinating thing is we can calculate this value in parallel if we wanted to get the value of the ampersand as well. Again, that's going to be the second row and the second column. And we can calculate these values, again, independently of each other. So since CPU cores can only be in the tens typically, and CUDA cores can be in the thousands, if not tens of thousands, we see that taking this matrix multiplication and simply altering it to work in a more parallelizable context is super duper trivial. In fact, we call this algorithm embarrassingly parallel because of how easy it is to parallelize. In fact, here are two code samples. I hope it's big enough for you guys. But on the top, we have the very simple serial implementation of matrix multiplication in C++. We have three loops. The first loop iterates through all of the rows in the first matrix. The second loop iterates through all of the columns in the second matrix. And the inner loop iterates through each of the elements across the row and the column, simply takes a dot product, accumulates it in a variable called sum, and then at the very end, assigns it to a value in the C matrix. Whereas if we look at the bottom example, the CUDA version, the outer two for loops are completely eliminated. But rather, we take this simple program and launch thousands of instances of it at the same time. And then each instance has its own I and j value, which then perform this inner for loop, again, completely parallel of any other instances. And this is how easy it is to parallelize matrix multiplication. Now, naturally, in industry, the bottom implementation is a very inefficient implementation, even in the world of parallel programming. We're not using any shared memory or trying to maximize cache hits or anything, but for today's purposes, it should illustrate how easy it is to parallelize code that typically takes 3 for loops down to just 1. So, I mean, we use GPUs for deep learning, so why not just stop here? Well, in this new world of LLMs, where models such as Llama 3.1 has a 405 billion parameter version, it's simply not possible to train it on one GPU. In fact, this model, just to run inference in the quantized version, takes over 800 gigabytes of memory. So for context, any consumer-grade GPU can have anywhere from 16 to 24 gigabytes of VRAM if you're lucky. And then data center or like enterprise class GPUs can have up to 80 gigabytes. So even buying those $40,000 GPUs from NVIDIA that have 80 gigabytes of VRAM, you'll need at least 8 of them to be able to properly run inference on these new LLMs. And training them is a completely different problem statement because now we're dealing with so much more, such as optimizer states, dealing with the data loading efficiently, making sure checkpointing is running as intended, and simply put, one GPU is not going to cut it. So it's our job as machine learning engineers to make sure that the researchers can do what they do best, research, and we build the infrastructure that allows them to do so as efficiently as possible. So before we dive into our first parallelism strategy, or the way to speed up training even more, let's review the basic training loop. I trust all of you guys have tinkered with PyTorch and are very familiar with this loop, but I simply want to place these vocab words in your guys' L1 cache because I'll be retrieving it throughout the rest of this talk. So first, we have the forward pass. So for the inner for loop, where we pull the values from our data loader, we'll simply take the inputs, pass it through our model, which is the forward pass. Then we'll take our loss function and calculate the loss. Then we'll perform backpropagation, which, remember, computes the gradients for each one of our parameters in our neural network. And remember, these gradients indicate how much we need to tune each parameter in order to minimize this loss function. And then once the gradients have all been computed, we can take a step with our optimizer, which essentially updates the parameters of our neural network with these calculated gradients. So the goal is to be able to calculate as many gradients as possible, as fast as possible, to take as many steps of our neural network parameters. And this, in the long run, we're hoping will converge to a model that's able to predict or generate images or whatnot. So let's jump over to our first parallelism strategy, data parallelism. So why not start off by giving our lonely GPU, very simple, just another friend. So now what we have are two GPUs, each with their own copy of the model. So we take this neural network, we duplicate it, and then we place it in the VRAM of GPU 0 and the VRAM of GPU 1. So the way training progresses is very similar to the training loop we just covered. However, there's a key difference when we calculate the gradients. And I have a little animation that illustrates this. So like I said, first step is to clone the model. Then for each GPU's forward pass, we feed it a different batch from our training data. We calculate the loss, backpropagate, and then this we'll see is where the difference comes in. We have to synchronize the gradients across the two GPUs. Because if we don't do any synchronization and simply step our optimizers, we're just training two versions of our model concurrently with no added speedups. This synchronization step is really what enables us to essentially double our training speed, because we're then doubling how much data we can process per iteration. So I'll show you guys the animation one more time to really showcase the power of data parallelism. Again, we do the forward pass, calculate the loss, backprop, calculate the gradients, and then we have to synchronize, which I'm going to dive deeper into in just a sec. But this synchronization step is the key. So yes, we're adding some additional communication overhead, which as we'll talk about today is going to be our arch nemesis. However, the benefits far outweigh the cons of this additional communication. So let's dive deeper into what exactly this communication looks like. And this is essentially the language of GPUs and how they communicate with one another. It's called NCCL, which is pioneered by NVIDIA and stands for NVIDIA's Collective Communication Library. Here I have three primitives that GPUs use to talk to one another. And on the top left, we have the all-reduce, which, as we can see, each rank, or GPU in this case, has a different set of anything, like data, gradients, parameters, it could be anything. And then the result is on the right. So all gather, you can see in the diagram, is on the top right, and then reduce scatter is on the bottom. So I have a question for you guys. So given this animation that we just saw, where we take the gradients of the two GPUs and we synchronize them, and then we make sure that both GPUs after the synchronization step have the same copy of these synchronized, or in this case, averaged gradients, which of these three NCCL primitives do you guys think is used? And this is actually an interview question for me a couple weeks ago. So stuff like this is knowledge that companies are looking for if you guys are ever interested in this space.
Combining the gradients, you said?
Yeah. Yeah.
I would guess all reduced.
How come?
Because the mean is just the sum divided by the number, so you can just use all reduce to get the sum and then divide by the 4 in this case.
Exactly, yes. All reduce is the correct answer here. So again, this all reduce operation is what allows us to utilize data parallelism to its fullest extent. Cool, yeah, nice job. Thank you for that. So now there's a huge problem with data parallel that we're going to try to circumvent throughout this talk. So can anyone guess what a huge limitation of data parallelism is? Yeah? Yes, so that is one problem because we're adding communication. But But as we'll see throughout all of our parallelism strategies, it's kind of non-unique. If we're adding multiple GPUs, we have to have communication. So our job is to minimize it. But there's another huge limitation of data parallelism. Yeah?
Is it like if your model doesn't fit online?
Exactly. Yep. So like I said at the beginning, the 405 billion parameter model, it requires over 800 gigabytes of VRAM for inference. So for training, it's going to be much larger. And in this case of data parallelism, if the model doesn't fit in each GPU's VRAM, along with the other parts of the training process, such as the optimizer states and the gradients and whatnot, we simply cannot run data parallelism. So it's good for small models, but in the world of LLMs, it's not going to work. So it seems like we have to do something else. We have to cut our model in some way. So that's where this next paradigm comes in. Pipeline parallelism. So as we can see, what's happening on screen is that if we have a neural network of 8 layers and 4 GPUs, why not just place 2 layers on each of the GPUs? And then the forward pass is probably going to be exactly what you're thinking. Yeah, here's the other animation. So we can see the forward pass starts from the leftmost GPU, and then we slowly pass the activations forward, with each GPU sending its calculated activations over to the next GPU in this sequence. So another question for you guys. What is a huge limitation of this strategy? Can you guys see it? Yeah.
There are two that come to mind. One is the communication. You have to communicate the activation to the next GPU. The second is that you have to have enough GPUs for example, if you're using 2 layers per GPU, you have to have number of layers over 2 GPUs, and also that each layer has to. I mean, even if you were to put just a single layer in each GPU, a single layer has to be able to fit on the GPU.
Exactly, yes. No, those are both definitely very valid constraints of pipeline parallelism. And this idea of layers not fitting on a GPU will be addressed by our next parallelism strategy. But there's one more thing that I'm also looking for in terms of a huge limitation. If I'm a big tech company and I've just dropped like $10 billion on like new GPU clusters, there's something really wrong with this animation. If you look at the bottom row, yeah? Exactly, yes. That is a huge limitation of pipeline parallel, where if I have 4 GPUs, only 25% of them are being used at any given point. And given that I just spent $10 billion, I'm not going to be happy with this. So there are going to be other techniques that build on top of pipeline parallelism to try to optimize for this, namely micro-batching. So what micro-batching is going to do, as we'll see in this animation, is that it takes each batch and divides it into further smaller batches. And now, as we can see in the animation, we're able to utilize more of the GPUs for a larger period of time. But this idea of some GPUs still not being fully utilized at all points in time is still valid. So in the GPipe paper, which pioneered this concept of micro-batching, on the bottom right, we can see is called the bubble. And when we're using pipeline parallelism, our goal is to minimize this bubble as much as possible, because idle GPUs means that we are falling behind in this race to build the best LLM in the market. But also another issue with pipeline parallelism is that it may even lead to like uneven splits. If our model architecture isn't too conducive to being split vertically, we can see that some GPUs may be assigned more work than other GPUs. So this is just mentioned, but another issue with pipeline parallelism is that one layer itself may not fit in the VRAM of any given GPU, in which case we have tensor parallelism. So pipeline parallelism, we cut the model vertically, but what happens if we cut it horizontally? And that's exactly what tensor parallelism aims to solve. So what's happening here essentially is that at the matrix multiplication level of each of these layers, we essentially split the matrices across different GPUs. So what that looks like is on the screen, we have 2 ways of implementing tensor parallel, which is on the top column parallelism and on the bottom row parallelism. So if we look at the left side of the screen, we'll see that x times a equals y, a simple 2x4 and a 4x2 resulting in a 2x2 matrix. So on the top, If we split the A matrix by its columns and duplicate the X matrix, we have two independent matrix multiplication operations, after which we can concatenate the results to yield us the original result that we would have gotten had we done this operation on just one GPU. And naturally, with matrices of this size, we wouldn't want to do tensor parallel, but as these matrices get bigger and bigger, we can see that there's a huge value add for tensor parallel. And for the bottom example, if we wanted to split the A matrix by its rows, we would split the X matrix by its columns. And again, this would give us two 2x2 matrices, which we add. And again, we are given the same final result that we would have gotten had we just done a simple matrix multiplication on just one GPU. So that is essentially how tensor parallel works. So let's jump back to this world of data parallel, or as sometimes it's called distributed data parallel if we're using multiple processes. I mentioned earlier that with data parallel, we need the model to fit inside of each GPU's VRAM, which simply is not an option that's on the table when working with LLMs or any other large model. So there have been other advancements that build on top of data parallel that try to circumvent this limitation, namely FSDP and DeepSpeed. The former is pioneered by Meta and is very tightly integrated with the PyTorch library, which is also headed by Meta, and then the latter is by Microsoft. And with DeepSpeed, they've also added this zero redundant optimizer, which helps shard the optimizer states, gradients, and the parameters across several GPUs, allowing us to still use data parallel, but circumvent these memory limitations. So both of these libraries are pretty similar, just implemented differently by different companies, but they each have 3 levels of optimization. The biggest one, which is just the first level of optimization, is by sharding the optimizer states, which I'll show you guys an animation of in just a sec. Second is sharding the gradients and the optimizer states. And finally is sharding all parts of this machine learning training process, namely the optimizer states, the gradients, and the parameters. So to understand why sharding the optimizer states is so important, let's do a quick review of the Atom Optimizer. Has anyone here used the Atom Optimizer or learned about it in class? Okay, cool. So it seems like most of you guys. Okay, awesome. So I'm not going to jump into the theory behind the Atom Optimizer, but the main thing to note is that for each parameter, we need 2 additional numbers, namely the momentum term and the variance term. And these 2 numbers combined with the gradient is what allows the Atom Optimizer to take steps, allowing us to hopefully in the long run minimize our cost function. So if we have a model that has 405 billion parameters, we need to add 810 billion numbers more, which are part of the optimizer states. So naturally, we're essentially just tripling our memory usage when we're using Atom, and this obviously is definitely not going to help us. So let's take a look at FSDP. So how this works is that we're still in the world of data parallel. So each GPU gets its own set of data, but now instead of duplicating the model, we will make sure each GPU is responsible for simply a portion of the model, similar to pipeline parallel, but there's a huge difference here. During the forward pass, we don't just give the data to GPU 0, which then passes the activations to GPU 1, which then passes it to GPU 2. Rather, let's say we have 4 GPUs. The way it works is that we cut the model up into quarters, and GPU 0 is responsible for the first quarter. However, all 4 GPUs will participate in the forward pass at the exact same time. So how it works is that GPU 0 will broadcast its quarter of the model to the other 3 GPUs. And since each of the 4 GPUs has its own bit of the data, each GPU can concurrently perform the first quarter of the forward pass. And then after that, GPUs 1, 2, and 3 will delete its copy of GPU 0's model parameters, and then GPU 1 will then broadcast its quarter, which is the second quarter of our model, to the other 3 GPUs. So now the second quarter of the forward pass can commence. And as we can see on the screen, after we take the data, right before we start the forward pass, there is a gather weights stage, which again is the all gather nickel primitive. So I'm pointing at the bottom image I guess it's kind of blurry, but like where it says all gather right after model shard. So like I mentioned, what's happening here is that for each quarter of the forward pass, the GPU that's responsible for that quarter of the model parameters will broadcast its quarter to the other 3 GPUs. And just like this, the forward pass is complete, and the same process happens during the backwards pass. So the crazy thing is we're actually not introducing any additional communication overhead when doing this, when we're not sharding the parameters. And the reason for this is, like I mentioned, in DDP, we're using the all-gather nickel primitive. But in the bottom right, if we take a look at what exactly is happening under the hood, an all-gather, or an all-reduce, is simply a reduce scatter plus an all-gather. And this is great because for no additional communication cost, we're able to now fit these models in memory, which is exactly what we're trying to do. So that's FSDP. DeepSpeed, again, is very similar. There's those 3 levels of optimizations that I talked about. First is sharding just the optimizer states, which is the biggest place where our memory goes. Second is the optimizer states and the gradients. And finally is sharding all 3 parts, the optimizer states, the gradients, and the parameters. The nice thing about DeepSpeed is that they have a really neat video. Microsoft has made this where it actually showcases step by step what exactly happens during this 0-3 or all 3 optimizations training process. So I'm not going to like walk you guys through it now, but I highly recommend that you guys check it out. So just to rehash what I talked about, as we can see, each of the 4 GPUs are responsible for a quarter of the model. And then I guess I can quickly go through the forward pass with you guys. So what happens is GPU 0 will essentially broadcast its blue parameters to all of the other GPUs. The forward pass continues, and then the other 3 GPUs delete their copy. And then right now what we're about to see is GPU 1 going to send its model weights to the other 3 GPUs. So yeah, there's the deletion. I guess it's not playing, hang on. Oh, I see, yeah. Okay, it's not playing, but essentially what just happened was, oh yeah, oh my cursor works, sick. So GPU 1 takes its model parameters and broadcasts it to the other 3 GPUs, and then the forward pass commences like normal. And like I mentioned, the same process happens during the backwards pass, and again, the whole goal here is to be able to save on memory. So these are the 3 fundamental parallelism strategies that are very commonly used in industry. And the next question that you guys might have is, what do I do with this? Like, what is next with this very simple overview? Well, I would recommend checking out papers that combine these different parallelism strategies and try to squeeze even more performance out of our GPUs. Because I outlined the cons of each of the 3 strategies, and the nice thing is the pros of each can almost complement the cons of the others. So if we can combine all of them, there's actually a lot of upside to be experienced. Another recommendation I would really encourage you guys to potentially think about is to actually try to use these different parallelism strategies. It may not be common for most people to have access to multiple GPUs, but I think renting compute, or if some of your buddies also have gaming computers, I think setting up a quick LAN party, but instead of playing games, doing machine learning, would also be pretty fun. Because it really allows you to take this, for example, Hugging Face's Accelerate library, or PyTorch's built-in distribution tools, and really try to see how you guys can serve larger models across multiple GPUs. Question?
Do you know if JAX, or specifically JAX's PMAP feature, also natively supports DDP and FSDP?
I'm actually not sure. I've never used JAX before. It's pretty much Google only from what I've heard. But I feel like most other tech companies tend to use PyTorch, if not TensorFlow. So yeah, I'm sorry, I don't know.
Does TensorFlow natively support DDP and FSDP?
Yeah, DDP for sure. I'm not sure about FSDP. I'm sure there's some open source library built on top of TF to make it work. But I guess I use PyTorch at work, so it's the one that I'm most familiar with. Yeah. So the Galvatron paper is probably where I would consider starting, because it introduces this concept of ND parallelism, or essentially splitting up the model not just once or twice, but an n number of times. So if we have a very massive LLM and let's say 16 or 32 GPUs, we could combine data parallel, tensor parallel, and pipeline parallel to split up the model multiple times across each of these GPUs. And it does this with a very neat dynamic programming algorithm that I recommend you guys check out in the paper. But essentially how it looks like is, let's say we have this massive model and 8 GPUs, we could potentially split it horizontally, vertically, and duplicate the entire thing across another group of 4 GPUs. So then we have this giant setup of 8 GPUs all working together to train this larger neural network. Several more papers that I would recommend checking out if you're really interested in this space. First is breadth-first pipeline parallelism. It does some neat tricks to combine data parallelism with pipeline parallelism. And don't worry too much about writing all of this down. I'll have Archon send out this PowerPoint after this talk. But the cool thing about breadth-first pipeline parallelism is that with data parallel, you're oftentimes limited to how small you can make the batch. And if the aggregate batch across all the GPUs is too large, it requires more training steps for the model to converge. So we can't always just rely on FSDP and DeepSpeed. So combining pipeline parallelism with data parallelism yields some more potential benefits that this paper explores. Second is the megascale paper, which was actually written by some of my colleagues at ByteDance. And here they talk about some of the challenges that they ran into when scaling LLM training to more than 10,000 GPUs, a feature that ByteDance heavily relies on given all of the ML services that it serves to its users. Some of the things the paper talks about are the new monitoring techniques, the redundancy techniques that ByteDance has come up with to make sure that even if one GPU fails during training, the entire training of more than 10,000 GPUs is uninterrupted. I think one thing I found fascinating from this paper is that there's quite a noticeable variance in the same model of GPU's performance when we scale it up to more than 10,000 of them. Some GPUs are just noticeably slower than others, even though they're the exact same model from NVIDIA. The third one is Megatron LM, and this was, I think, written by NVIDIA, where they combined pipeline parallel and tensor parallel to train LLMs, again, across a large number of GPUs. The fourth one is gpipe, which I've mentioned. It introduced micro-batching in pipeline parallel. And the bottom two are about the zero redundancy optimizer that DeepSpeed has introduced. And the final one is PyTorch's FSDP paper, again from scientists at Meta. So again, if this is a space, if distributed machine learning is a space that you're very interested in, I highly recommend that you guys check out these papers. So, and there's also a lot of other orthogonal optimizations that MLEs often have to think about when training and running inference on models. I'm not going to dive into these too much because it's outside of the scope of today's talk. However, again, if this stuff really excites you, I highly recommend you guys check out these topics. The first is quantization. So a high-level overview, essentially what it is taking these numbers, whether it's the gradients, parameters, optimizer states, and shrinking them to a lower precision. I'm not sure if you guys remember the IEEE standard for representing floating point 32 numbers, but essentially, if I recall the numbers correctly, the first bit is the signed bit, and then it's 8 bits for the exponent, and the remaining 23 bits are the mantissa, right? So the IEEE standard for floating point 16 actually is 1 bit for the signed bit, 5 for the exponent, and then the remaining bits are part of the mantissa. So the problem here is that by reducing the number of bits for the exponent, we are severely limiting the range of numbers, the range of floating point numbers that we can represent when running training. And oftentimes, this hurts training. So Google came up with this concept of the bfloat 16, or the brain floating point number, which again uses 16 bits to represent all of these numbers, but increases the exponent back to 8 bits, and then the remaining 7 bits are now used to represent the mantissa. So yes, we're losing some precision, but now we're getting back the range of values that we can represent with 16 bits. The nice thing is it's incredibly easy to convert between or from FP32 to bfloat 16. We're simply truncating some bits at the end. And even though we're losing precision, the nice thing is that this oftentimes acts as like a regularization force when training. So sometimes it actually helps convergence. However, we don't always just want to naively cast down to BF16. there's this concept of automatic mixed precision, where some numbers are in FP32, some are in BF16, and we run training. So again, this speeds up training while giving us some memory benefits as well without hurting performance at all. The final two are regarding attention, the crux of the transformer architecture from 2017. The first is flash attention, which is a more I/O-aware method of running attention. I'm not sure how familiar you guys are with attention, but essentially we have the key matrices, the query matrices, and like the value matrices. And the problem is this naive implementation doesn't rely on the caching that's built into our CPUs and GPUs. So flash attention aims to utilize this cache hierarchy more optimally to increase the number of computations actually, but to decrease the pressure it places on memory. Because these days with our GPUs, we are more memory bound than compute bound. Our GPUs are faster than they are able to store a lot of values at the same time in VRAM. So if we can shift away some of the pressure from memory back to the computation portions of our GPUs, technically on paper it's slower, but in real world wall time, we can actually see speed ups. And page attention is a very neat way of storing these attention values in the memory of GPUs that aims to minimize fragmentation. So again, slightly outside of the scope of today's talk, but I wanted to share them because these parallelism strategies aren't just the end-all be-all, but there's a huge world of different optimizations that we can do given any one specific algorithm or set of data. And I really feel like this subfield of machine learning is probably the most blossoming right now because like I mentioned earlier, these algorithmic advancements come only 5 to 6 years and data preprocessing is like kind of like very boring in my opinion. So like this is where it's at, guys. So anyways, how to stay in touch, LinkedIn, YouTube channel. Some of my most popular videos are about like machine learning naturally. I've built my own computer, installed Linux and set it up for ML stuff. One of my videos about optimizers has done pretty well. So if you guys are interested, definitely check that stuff out. However, I wanted to open the floor up to questions about what I do at TikTok, anything that we talked about today, just, yeah, anything. What's up?
I have two questions.
Yeah.
My first one is that I thought your background was really interesting as a computer science, data science, and economics major. What I was wondering is, what are some market failures or market inefficiencies that you think machine learning could address, and what are some market inefficiencies or market failures that machine learning could create?
Wow, that's a very deep question. Thank you for asking that. The funny thing is I wasn't really too like into economics in college. So this is more just off-the-cuff thinking about where ML truly has benefits in terms of the economy. I think naturally, increased productivity is going to be a good thing for the economy because it's going to drive down prices. It's inherently deflationary. So I think in general, across most markets, it's going to have a net positive impact. But I think the markets where it could hurt in the short term are the ones where these new AI models or these new AI agents that are coming out are displacing human labor. So I think in the short term, we're definitely going to see some market failures in the sense that like, short term as in like 10, 20 years. I think way past that, the market will have solved for this. But I think the next 20 years, we could definitely see like huge swaths of employment just disappear. And honestly, programming is definitely like on the table here with all these new advancements that LLMs are able to now like code and stuff. So very interesting question. You had one more, I think?
Yes, another question I had is, for hyperparameter, are there any specific parallelism algorithms specifically for example, like one thing I was thinking is maybe you could use this as a way to like dynamically tune for layer sizes, even like during training, maybe. But I don't know if that would like I should probably just say the question. Are there any specific parallelism algorithms for hyperparameter?
I'm sure there are. That's actually a really interesting point you bring up. I haven't read any papers in that space. But yeah, if I run across any, I'll give them to Archon to send out to the club. But that's a really good point, actually. And I'm sure there's research being done in that area.
Thank you very much.
Yeah, no, thank you for asking. Any other questions, guys? Yeah?
Are there like practical approaches for like learning this stuff hands-on? Because like I would assume like most people don't like have access to a couple of GPUs lying around.
Yeah. I actually like came across this GitHub repo that like had like puzzles literally on this topic. So again, I'll send that out to Archon. It was kind of interesting. It's like this guy. He seems pretty smart, but like he like made like this little Python library and like a little set of like challenges to like use like all reduce and like all gather and stuff to like complete some like puzzles. So I haven't gone through it myself. I've started it, but I do think like it seemed promising and like a good way to like get like a hands-on approach. I think another one, like implementing data parallel from scratch on your own, is also like on the table. I haven't tried this either, but you could potentially use Docker containers to just use one GPU, but then treat each Docker container as its own separate GPU. So like I think that's a very like accessible way to potentially try these different strategies. And also, like I said, like renting compute's pretty cheap, although like y'all are college students, so I'm not gonna tell you guys to spend money. But I also like do think that like grouping together like gaming computers is, again, very like accessible to like college students. Yeah, no, good question though. Any other questions, guys? Yeah?
I guess like there's like a bunch of different like methods for like more efficient computing. Like I know like page attention is one, flash attention is one. There's also ones that get released that like no one uses but are just as like good. For example, like I believe SG-Link came out at the same time as like the VLL project, which was just like page attention. Like, but I feel like no one uses it because it isn't as well publicized or it isn't as easy to use. So like when doing this sort of thing, like what do you think is most important to actually get people to use it?
Right, yeah, I know, that's a very good question. Like one of the things that's mentioned in like the breadth first pipeline parallel paper is that they really worked on making it accessible to researchers. Because the truth is, researchers, like they don't care about this. They just want their ML models to train. So I do think there's an advantage, let's say like with FSDP, because Meta worked on it and they're able to tele-integrate it into PyTorch, where that's very easily like accessible to researchers and it's very publicized because it's created by the team that built the original open source package. So I do think there's a huge advantage for when these big companies like Meta or like Microsoft release these optimization techniques. And then second, if you can build it on top of like PyTorch or TensorFlow even, I think that's another easy way to make it more accessible to users. But ultimately, I think this boils down to like a product design question. Kind of like the iPhone of like how do we make it like very intuitive and easy to use. So the researchers don't have to like think twice. They can simply, so I guess like take for example like Hugging Face's Accelerate library. To simply start a very naive DDP loop, all you need to do is just add 4 lines of code and then like pretty much any simple machine learning model can then be trained on like n number of GPUs, which I think is really fascinating that it only takes 4 lines. So I think to like come back to your question, improving the user experience I think is definitely the first step. And I feel like in this world where like everyone's like, oh, but like speed, ultimately it really comes down to user experience. So yeah, good question, thank you. Yeah?
It's kind of in a similar vein. Like I know there's a lot of hardware specific like issues that come up when trying to deploy different models or use like even let's say like different optimizations. Like as like in industry, I guess, like as your day-to-day job, like how do you guys make sure that the hardware is compatible with the software and whatnot? Like what are the facts?
Yeah, and again, that's a very good question. And the Megascale paper actually addresses some of that, where like some of the challenges they ran into was that some of these NVIDIA cards, again, like from the same generation, are very inconsistent when it comes to performance. So there are a couple of things. There's also work being done in writing compilers that transcend any one vendor. So stuff that compiles like C++ code into CUDA code, into the code that runs on AMD GPUs. I forgot exactly what it's, I think ROC M or something like that. There's research being done where like just one code base runs on multiple vendors of GPUs. There's stuff like Triton, which actually bypasses the CUDA layer. So you write Python code, and then it compiles directly into PTX, which theoretically with some additional optimizations should be able to run on any type of hardware. So yeah, I mean, there's definitely work being done in this space, and like I think a lot of companies are thinking about preventing vendor lock-in. So even like Microsoft is like working on their own chips, so is ByteDance and stuff like that. Yeah.
Can you tell us a little bit more about your role as ML systems engineer at TikTok? Like, what does that look like?
Yeah, definitely. It's your typical like programming job, like nothing too fancy. But like I mentioned at the beginning, the 2 core products that I work on, First are the actual machine learning platforms, so adding features to make the quality of life better for our machine learning engineers. So it's your typical like application. So there's like the front end, the back end, databases, there's all of that stuff. But also the second part of my job is working in Python, adding more features to our training framework that our LLM researchers use. So making sure checkpointing is robust, making sure that when the data is being loaded in, it's being done so as efficiently as possible. Because again, when we add parallelism and multiple GPUs, stuff like this is of the utmost importance. Because if one GPU fails, we don't want all that data or like all that progress to be lost. So strategically checkpointing across multiple GPUs such that if one fails, all is not lost is very important. So it's like adding features like that to our internal training framework. Yep.
You mentioned before that you built PC. I don't know if you're into gaming or PC gaming at all, but one thing I'm kind of interested in or want to get interested in, I don't really know much about it, is machine learning for graphics and stuff. I was wondering, are there any gaming systems or any research into using AI for graphics in video games? And if so, could we potentially see multi-GPU gaming PCs incorporating some type of parallelism to make these types of systems faster?
That's a really good question, actually. So to answer that second half first, about using multiple GPUs concurrently for gaming, NVIDIA's had that technology with SLI, right? But they kind of like killed it. So this is less of a machine learning problem, I think, and more just about like a graphics problem and how these companies want to implement the hardware itself to support multiple GPUs while gaming. So if I recall correctly with SLI, each GPU alternates in rendering a frame of the game. So theoretically, you're like doubling throughput here. But in terms of combining video games and machine learning, one paper that really blew my mind recently was the idea of using stable diffusion to just act as your game engine. So there's no physics simulations or like player state that's being kept track of. It's just one end-to-end machine learning model that takes in player inputs and outputs a frame. So the paper showcased Doom running in this weird like game engine that allowed the player to just play, I think at 20 frames per second. So definitely not real time yet, but definitely like a very promising direction of research. So that's a really good question. Yeah, I think combining stable diffusion and like graphics like has a ton of potential and upside in the long run. Actually, one more thing with video games. With the advent of Gen AI, there's also this new concept of having LLMs backing up these NPCs. So I went to NVIDIA GTC earlier this March, and one very intriguing presentation that I listened in on was about this company that's working on like implementing Gen AI into video games. So one example that they shared was that one of the tasks in the video game was to like convince a bunch of NPCs to flee a village because like a flood was coming, and this was just your job to like save the village. And because each of these NPCs are backed up by a Gen AI model, you're now literally talking to them, trying to convince them to like move, like as if like they're human, which is kind of crazy and definitely adds a new dimension of immersion to the video game. So one strategy that they were sharing that was employed by a player was to convince one NPC to convince the other NPCs. And that just like increased like the player's leverage to like save like the village and stuff. And like that's a very like small example, but like I really think it illustrates the true potential of like combining like Gen AI and video games.
I think I saw, was that paper from DeepMind by
Yeah, so the stable diffusion one, yes. Yeah.
I see. And I mean, you just really can't get deep learning on anything. I think that would also be a cool thing down to a game like Breath of the Wild or something.
Yeah.
The thing I really like about that game is that you can basically do like whatever you want.
Mhm.
It doesn't really stop you from doing a lot, but like you're still limited with like the NPCs. Like you only have the basic dialogue.
Naturally, yeah.
Yeah, if you could do something like that with like Breath of the Wild or Baldur's Gate 3 or something like that.
Definitely. Actually, one more thing about video games is I'll get to you in a sec. But like, there's this concept of like upscaling the frame as well. I know like I'm really into video games. So, like machine learning in video games are like my dream come true. So the final like application of like ML in video games that I found really fascinating was to use a model that's running locally on device to upscale the frame. So then the GPU is responsible for simply rendering a game, let's say at 1080p, which is easier for it, and then using the tensor cores on the GPU hardware, we're upscaling it to 4K. That's one application of like DLSS or like, I forgot what like AMD's version was. But then there's also this concept of frame generation where I take 2 frames outputted by the GPU and I use generative AI to generate the middle frame. So theoretically I could be upscaling and generating new frames for like maximum like frame rates and stuff, which again like I think is just absolutely fascinating. But a question?
It's not a question.
Yeah.
It's still like related to like machine learning and gaming.
Mm-hmm.
The one really cool paper that just came out is about they found a way to scale nerves like using more GPUs. Because so normally like when you train a nerve, usually you run it on like a single GPU.
Yep.
And they came up with a way to like scale on multiple GPUs, and they were showing like demonstrations of how you can basically simulate like an entire like city like using a nerve. So
Mm-hmm.
it's pretty like interesting applications.
Right. I think I've seen that paper. But yeah, no, I think like neural like radiance fields are really cool. Again, very applicable to like the world of video games, whether it's creating like 3D models really efficiently or just new game worlds. So yeah, no, great point. Thank you for bringing that up.
Do you remember the name of the paper?
Nerf XL.
Nerf XL.
It's from Gonzalez.
Okay.
Thank you.
Yep, question?
I was curious about ByteDance's like tool chain for sorts of distributed models. Like, do you guys use like automated distribution like iMine or Orthorobot or something like that? And sorry, one more thing. How do you strike the balance between like having like a REPL sort of like iteration of models versus like submitting a job and then having it trained for a while?
That's a very interesting question. So I think that's more, so the second part's more on the research side of things, which I'm not too familiar with, so I'd want to give you information that's misleading. But like the first, in terms of like the automatic parallelism stuff, we have like an open source library that we're working on called vscale that like implements the ND parallelism automatically. So you just give it the model architecture, your network topology, and then it'll automatically find the best configuration of like data parallel, pipeline parallel, and tensor parallel to like train the model optimally. But I'm not sure if we use like the two tools that you actually mentioned. But like conceptually, we do use like similar ideas. Yeah. Awesome. Any other questions, guys? Cool. Yeah.
If anyone has any questions, feel free to
Yeah.
ask.
Definitely reach out.
Like, one-on-one. But yeah, all right. Thank you.
Thank you, guys. Thank you.